A fully loaded supertanker displaces 200,000 tons. Its anchor weighs 20. That's 1/100% of the ship's mass. By every engineering intuition, this shouldn't work. And here's the reality. The anchor alone doesn't. What actually keeps a vessel this size from drifting involves something most people never consider. And it starts with over 100 tons of chain that never leaves the seafloor. A Greek sailor, 2,000 years ago, faced a familiar problem: how to keep his wooden galley from drifting overnight. His solution was a hollow basket, packed with stones, lowered overboard until it settled onto the seabed. The logic was simple. More weight should mean more grip. But the numbers tell a different story. Even a 2-meter stone basket, loaded to the limit, rarely held more than 4 tons before sliding across soft sand. That is barely enough to resist a summer breeze, let alone a sudden squall. The ratio is stark. For a trading galley displacing 300 tons, the anchor's holding force was barely 1% of the ship's mass. This weight-based approach persisted for centuries. Mariners added more stones, then switched to cast iron, always believing that sheer mass would solve the problem. But as ships grew, the gap only widened. Modern supertankers can tip the scales at 200,000 tons, yet their anchors weigh just 20, about 0.01% of the ship's mass. If weight alone determined holding power, these vessels would never stay put. The math is unyielding. A 20-ton anchor, scaled up from ancient logic, would be hopelessly outmatched by even a modest current or gust. The Greek sailor's basket was doomed by the limits of friction and the physics of scale. It could only grip as hard as its own weight pressed down. No matter how many stones were piled in, the anchor's ability to hold was capped by a simple equation: force equals mass times gravity, and friction can only do so much. The real breakthrough would not come from more weight, but from a change in geometry and the way forces are delivered to the seabed. A Roman shipwright along the Tiber would have noticed the shift from stone baskets to iron anchors, but also the new reliance on geometry. By the 1st century BCE, flukes and stocks replaced brute weight with calculated design. Modern anchors push this further. Each fluke is engineered to shear off cleanly along a plane set at 30 to 35 degrees to the shank. This isn't a flaw, it's a safeguard. If a surge pulls too steeply, the fluke breaks away before the chain or hull can be torn apart. The anchor survives by giving up its grip in a controlled way. But the real power lies in the chain. On a supertanker, a single link weighs over 120 kilograms, and the entire deployed chain can top 100 tons, far outweighing the anchor itself. This mass pulls the chain into a catenary curve, pressing it flat against the seabed. The tension at the anchor stays almost entirely horizontal. Any upward force, anything that might lift the anchor, gets absorbed by the chain's bulk. The flukes are shaped to dig in deeper as the horizontal load increases, while the shear plane ensures that a dangerous vertical force never reaches catastrophic levels. The chain's weight and the angle it forms with the seabed decide whether the anchor holds. A shallow angle, created by letting out more chain, keeps the flukes gripping sideways where they're strongest. If the angle rises even slightly, the risk of fluke shear jumps. The chain must always outweigh the anchor, every link built for mass and controlled deformation. The anchor's true strength is the iron leash that holds it down. String. A ship's ability to stay put depends on more than just the mass of the anchor and chain. It hinges on geometry, friction, and the precise length of chain paid out. The key variable is scope, the ratio of chain length to water depth. With a scope of 3:1, the chain forms a steeper angle, about 30 degrees, where it meets the seabed. At this angle, much of the pull lifts the anchor, slashing its ability to grip. But increase the scope to 5:1 or even 10:1, and the angle drops to 15 or even 7 degrees. The effect is dramatic. Halving the angle doubles the horizontal force, pressing the anchor flukes sideways, where they hold best. This relationship is captured by a simple formula. Tangent theta is roughly 1 divided by scope minus 1. At a scope of 3 to 1, tangent theta equals 0.5, or about 30 degrees. At 10 to 1, tangent theta drops to about 0.11, or just 7 degrees. Even a small increase in scope can shift the pull from mostly vertical to almost entirely horizontal, transforming the anchor's holding power. Friction at the seabed is the final arbiter. The coefficient of friction, mu, ranges from 0.3 on hard sand to 0.6 in soft mud. The horizontal force, multiplied by mu, sets the anchor's ultimate limit. On a muddy bottom with mu of 0.5, a well-set anchor can resist a lateral load twice as large as the same anchor on hard sand. The system's strength is not just mass or metal, but the careful tuning of angle and friction to the conditions below. Even the toughest anchor fluke carries a hidden vulnerability by design. The alloys that form these massive plates, often 316L stainless steel or high-grade marine steels, are chosen for strength and corrosion resistance, but their real secret lies in how they're engineered to fail. Each fluke is scored with laser-etched grooves along a shear plane set at a precise angle, typically 30 to 35 degrees from the shank. These grooves act as stress concentrators, ensuring that if the pull on the chain turns dangerously upward, the fluke will shear off cleanly at about 90% of its rated strength. In fatigue tests, flukes with these micro grooves show a 10% drop in maximum shear load compared to unmodified steel, but this controlled weakness is intentional. As one naval architect puts it, the anchor is not the ultimate line of defense. It's a calculated fuse. Routine inspections are critical. Classification societies require ultrasonic scans of the shear zone and magnetic checks of every chain link, since a single undetected crack or corroded spot could trigger the entire system's planned failure point. The anchor assembly is strong, but never invincible. Its reliability depends on constant vigilance, not just brute force. Anchor drag remains one of the most unnerving risks at sea. On a foggy morning off the Pacific coast, a bulk carrier began to drift, its anchor flukes fouled by a dense bed of kelp. The crew watched as the ship's position crept past the 2-meter drift alarm threshold. In less than a minute, the chain's catenary flattened, the angle at the seabed rose, and the anchor lost its grip. The vessel moved almost imperceptibly at first, but the consequences could have been catastrophic. Modern regulations demand continuous anchor watch, but even the most vigilant crew can be outpaced by sudden changes below. Today, many offshore vessels rely on dynamic positioning instead of anchors. Here, the ship's location is tracked by centimeter precision GPS, and computer-controlled thrusters make corrections over 100 times per second. If the hull drifts even a meter, the system responds instantly. No chain, no flukes, just software and electric power. This digital mooring can hold a drilling platform steady in a 30-knot gale, where traditional anchors would be useless. As one naval architect puts it, the future of station keeping is algorithm, not iron. At sea, engineering reality is defined by ratios, not raw mass. A 20-ton anchor and its catenary chain counter 200,000 tons only when angle, scope, and seabed align. Today's supertankers rely on these precise balances, reminding us that small factors, calculated correctly, still hold the largest forces in check.